Mirko from ESR.
Okay, hello everyone. So today I'm going to show you my study, in which we investigate scattering dynamics using numerical simulation. The study is composed by two parts. In the first part, we tested the reliability of numerical simulation into propagate waves in heterogeneous medium. And about this part, I will show just an introduction. And then there is another part in which we apply this numerical simulation to study the scattering in a volcanic environment. So starting from the first one, we used a 3D spectral element solver to run some simulation in heterogeneous medium. And what we did is to compare our output with the theoretical expectation to understand how reliable are our numerical simulation. So just a bit of context. When waves propagate in a medium in which there are some heterogeneities, what we will see is a scattering and mode conversion of waves, which means that at any observation point, we will see that following the arrivals of the ballistic waves, we will have the so-called coda, which is a signal that is composed by phases which look random, even if they are not, and whose amplitude decreases smoothly over time. Now, so what we want to do is to compare our observation with the theoretical expectation, but so when we run numerical simulation, we obtain the ground motion, but in the theory, the theoretical tools that we have to interpret the scattering give us just the intensity or the average energy envelope at a given time and certain distance from the source, given the statistical properties of the medium. So this means that if we want to compare the two, we need to use a configuration that allows us to make this comparison. Here I'm just showing one of the simulations that we run for this purpose. We have a slice of the medium, so the medium is a 3D medium. Here I just shown a slice with the 10% standard deviation heterogeneity, so the fluctuation, and the heterogeneities are Laplacian correlated. So what we did is to put ourselves in conditions of complete symmetry. So we consider the full space medium, so no absorbing boundaries, only absorbing boundaries. A source which is isotropic exactly in the center of the medium, and then we deployed receivers on spherical shells at increasing distance from the center. We then were able to rotate the components of the receivers to retrieve the radial and transverse component, and then we were able to make averages and then to compare it with the theoretical expectation. So the first thing that we looked at is the scattering mean free path, which is the average length of interaction between waves and heterogeneity. So just by fitting the spectral component of the radial mean field, we were able to compute the mean free path. And the comparison with the theoretical expectation shows us that we have a good agreement, at least between 0.9 and 2.9 Hertz. So we then filtered our signal in this frequency range, and then we looked at the transition between the multiple scattering regime to diffusion regime. So we know that if we wait enough time, at some point we should get to diffusion. And we know that if we are in a 3D medium, we are expecting to see that the decay of the energy is proportional to this factor, which is exactly what we see. In this case, I'm showing also the decay for the displacement, strain, and rotation. Then the last thing that we looked at is the energy partition ratio. So when waves are propagating in a heterogeneous medium, we have also conversion in modes between S modes to P modes and the other way around. So we computed the energy partition ratio, evolution over time, and we compare it with the expectation of a radiative transfer equation, which was solved with Monte Carlo methods. And what is nice to notice here is that we were able to retrieve the full dynamics, so from the beginning up to the end. So we have a really nice match in this case. So this study is much more wider than what I'm showing here, but this I thought that could be a preliminary phase for the other project. So what we conclude here is that we run this kind of simulations. We were able to compare them with theoretical expectation, and then actually we can trust our simulation. So this means that we can use the simulation to study the scattering in different kinds of environments. And indeed, what we did in this study is to apply these simulations to a volcanic magmatic system, so to a plumbing system. The reason, so just a quick introduction about volcanic environments. In volcanic environments, we have several kinds of signals. I'm showing here only a few signals that are more meaningful for our analysis, but we will focus on mainly on tremors. Tremors are signals that are extremely long in duration. They can last up to months, and they can be considered as generated by sequences of low-frequency earthquakes. Now, the reason why we are interested in tremors is that, so if we look at tremors, in this case, for example, I'm showing a network-based frequency time analysis of volcanic tremors of a volcano in Kamchatka. What we see is that when we do this kind of analysis, we see that in tremors, there are some frequency component which are consistent in time. So the current understanding of this consistency relates them to resonance effects in full field cracks, which means that it's something extremely local related to the source area. So there is some local resonances in the source area. But there could be many factors that could generate some sort of stability. And what we would like to do is to understand if this sort of stability could be related even to scattering effects. So just a bit of an introduction. So the scattering, the interaction of waves with heterogeneities depends in general on the wavelength and the correlation length of let's say in the impedance contracts of a certain area of the medium. But the scattering can affect the frequency content in many ways, in two ways. First is that we could have an interference due to multiple paths, which means that from one source, waves are just getting to a certain receiver doing different paths, and so we can have a sort of interference in the frequency domain, which means that so it's related to the path. And then we could have another effect which in some areas, due to the characteristics of the medium, we can have some trapped waves, which is a kind of sort of resonance-like thing. Okay, and so, okay, now that we know that there are many effects that could affect our spectrum, we need the first thing that we need to do in order to run this kind of simulations is to have a reliable model to describe a magmatic plumbing system. Otherwise, our analysis will not be reliable. So what we use is a model that was obtained by Oleg Melnik, which is contributed to this work. The model that I'm showing is here we can see the evolution. It comes from fluid dynamics simulations and is obtained by injection of dikes and seals without eruption in a granitic crust. So we can see the evolution over time. But it's important to highlight that this is a model for the melt fraction, which means that if you are familiar with numerical simulation of waves propagation, we need to have a model for Vs and Vp, velocity and density. So we had to convert one of these frame, in this case, for example, the last one, to a model to have a Vp and Vs model. So the model that we obtain at the end is this. I'm showing here the one for the S velocity. I'm showing also the settings of the experiment. So we have 5 receivers at the free surface, and then we have a grid composed of 7,800 sources spaced on a regular grid 100 meters. Now, if again you are familiar with numerical simulations, you may think that we run 7,800 simulations, which is not feasible because one of the simulations takes 5 days. So what we did is to use the reciprocity of the wave equation. The reciprocity is a property of the wave equation which allows us to exchange the position of source and receivers. This means that instead of doing 7,800 simulations, we could do only 5 simulations to get this setting. And I'm telling this because now I'm showing a movie of the simulation, and we will see a source that is on top. So here we have a movie for the vertical component of the displacement. We see that this is the area of a major scattering. I put also the model there. We see that a lot of scattering is produced in this area. So even at larger time lapse, we see that there are a lot of scattered waves. But also what is important to notice is that there are some areas in which it seems that there is more energy. So those areas are basically some dikes. Dikes are characterized by really slow velocity and also by big, large impedance contracts compared to the surrounding environment. So the first thing that I would like to show is something really basic, just to understand, just to look at some raw data. So we just select one of the receivers on top and the 4 sources. What I want to show here is that when we get inside the deep structure of the model, we get the more coda, so we generate more scattering, which is something that we saw also on the simulation before. But what is also important to notice is that, so here I'm showing the spectrum. Even if our source function is a Ricker function, which is extremely smooth, and even if we consider, for example, our first source, which is the shallower, so closer to the receiver, we obtain a lot of peaks. So our spectrum doesn't look smooth at all. And this, in this case, so again, we don't know to what those peaks are related, if it's a path, if it's a resonance. So we would like to investigate this aspect. And the first thing that we looked is that, so basically we put a lot of sources inside the medium, but we are not expecting that in volcanic environments the sources are distributed everywhere. We are expecting that they are localized in some features, for example, in some dikes, some silts. And so we did this analysis in which here I'm just showing an example, but we tested many silts, many dikes, and some other areas. So here I'm just showing a comparison between the spectrum retrieved at the 5 receivers for 2 sources. 2 are located in the sill, and 2 others are located in what we call the fast area, which is highlighted there. It's important to notice that at all the receivers we see a lot of peaks. But there is a huge difference between the fast area and the sill. So here we see that there are many peaks, but the peaks are different depending on the observation points of the receiver, which means that most probably those peaks here are related to path effects and not to something that is happening to the source. But when we look at the sill, we see that actually there are some stable peaks. We see a peak that occurs at all the receivers at both, so for both sources, at 2 and 2.5 Hertz. So this means that really unlikely this is related to the path. This most probably is related to a sort of local, really local resonance. In this kind of analysis, we consider something that was extremely localized in space, because we consider some sources, for example, that are 300 meters. Of course, when we did this analysis, we considered also wider distances, up to 800, 1 kilometer. But what we would like also to investigate is a larger area, if even larger area could trigger some sort of resonance. So to study, what we wanted to do is to understand how the energy of the scattering changes depending on the sources that we are considering. So we consider all the signal retrieved at the 5 receivers and all the sources, and then we compute the coda, the energy of the coda in the wide frequency range between 1 and 8 Hertz, and then we average it. And what we obtain, it's something like that. So we see that in the part in which we have more energy, more scattering, because the medium is more heterogeneous, we have more scattering. And then we try to relate it to the standard deviation of the velocity. And we see that there is actually a really nice agreement, but this is fully expected by theory, because we know that the energy of the scattering amplitude is related to the standard deviation of the velocity. So this is not something new, but it's important to see that we are able to see exactly this. So we see that there is a nice match. But then, before I say that the scattering depends on the wavelength and the size of the heterogeneity, so you may think, okay, between 1 and 8 Hertz, we are looking at wavelengths that span from hundreds of meters to kilometers. And indeed, what we did at this point is just to look at narrower frequency ranges to see what we see. So here I'm just showing an example, so 4 frequency ranges. And I would like to highlight 2 things. The first is that there are some areas, for example, the white area, in which we see that there is a lot of energy in a wide frequency range, at least between, for example, 2.5 and 7.5 Hertz. And then there are some other areas, for example, the red area, in which it appears that there is more energy only in some frequency range, for example, between 4 and 6.5 Hertz. So this seems that there are some areas that are deactivating based on the frequency we are looking at. And then the other thing that I would like to highlight is that, so before we looked at some sort of resonance inside really small structure, but here the areas which show a lot of energy are much wider than the single seal or single dike that we saw before. So there has to be another driving mechanism in this case. So in order to understand this, what we did is to understand how the spectrum changes when considering all the sources and the signal retrieved at the 5 receivers. So we compute the frequency of the maximum at all the receivers, and then we average it. And what we see is that there is a part on top in which the frequency is higher, which is close to the peak of the source function that we choose. Then there is a part of the medium in which it actually decreases, and then it increases again in a part in which there is more scattering. We try to relate it to the correlation length of the medium. So we compute the correlation length for each one of the source position in a certain range. That's why it looks a bit smoothed, let's say. And when we plot the correlation length as a function of the frequency of the maximum, we obtain something like this. So here we see all the points, and then we just bind the signal averaging in frequency ranges. And what we notice is that we see that when the correlation length is higher, the frequency goes lower, and the other way around. So this is something that could be expected by scattering, but in the scattering theory, but this is not, here the scattering is really complex. There is no statistical distribution of the scatterers. So this means that even in this kind of mediums, a source located in a zone characterized by a certain correlation length could be able to trigger resonance at a specific frequency. And this means also that, for example, volcanic environments are environments which are dynamic. So it means that, for example, because of fluid migration, they can change the source area. Means that also we can monitor the changes in the spectral components, and we could get some information about the health, let's say, of the source area in terms of fractures. So just concluding, we saw that there are, we ran this kind of simulation, and we saw that there are some, the frequency component of the spectrum amplitude can be linked to many mechanisms. One of them depends on the observation point, so interference of multiple paths. And then there are some features, some mechanisms that are not completely independent. So we have local resonance or wider resonance in area characterized by same correlation length. And so the conclusion is that studying the stability of the spectral features over time could provide us with information of the condition of the source area. And thank you.